For Unit 5, we're actually going to go back now to Chapter 2, and we're going to split this 2.1 into two parts. Part 1, we're going to be graphing quadratics given equations, and then what we're going to do is we're going to look at graphs and have to come up with the equations, so we'll have to work backwards. But for now, what our objectives are to review the three forms of quadratic equations, I should say, and how they are used. Alright, so this is key. We're looking at equations, and from those equations we're going to want to be able to find the vertex of the parabola and the x-intercepts of the parabolas that we're sketching. So here's some vocabulary for the chapter. Terms are expressions separated by addition. An example of this would be something like 3x to the fourth plus 5x plus 1, let's go 5x squared plus 15x minus 2. Okay, so this is something where we have 1, 2, 3, and then if I change this into a plus, then we would have to negate the following sign, 4 terms. So 1, 2, 3, 4 terms. These are expressions separated by addition. Polynomials include many terms composed of coefficients and variable parts of a non-negative integer, or in other words, a whole number exponent. So this would be an example of a polynomial because note that each one of these is a non-negative whole number. Now, looking at this one, we could go ahead and put an x here and then put it to the 0. So note that's still a whole number that's non-negative. So here, each one of our terms is going to be fulfilling that non-negative integer exponent. Further vocabulary, we're going to look at the quadratics. Quadratics are polynomials of the degree 2, or in other words, the highest exponent is 2. Our parent function for this looks as simple as this. We just have f of x equals x squared. So this is our label for a notation, or for a function. Functions again are just for every input, there's only one output, and you're going to see that every polynomial that we ever sketch, that's going to be the case, that for every input there's a predictable one output. Standard form, though, we're also going to expand on this because there could be transformations, shifts, and all these other things. So what happens is we could also write it like this. And there's other forms as well. So last thing of vocabulary here. We have a parabola. That's just the shape that any quadratic will make. So if you ever have a quadratic equation, you can expect the graph to be a U shape. Okay, so it's a U shape. Alright, the vertex is the central point of the parabola, a very important point because it's literally the central point. It also marks the maximum or the minimum point of that U shape or of that parabola. And then finally we have a line of symmetry. It's an imaginary vertical line in which points reflect over. It runs through the vertex. So I am going to go ahead and draw that line of symmetry. It goes right down through our vertex. Okay, and you can see that any point on this side is going to be directly reflected from the same distance and the same height on the other side. Okay, so if you know that you went back 1, up 1, then you would know that you're going forward 1, up 1 as well. Okay, so here, right here is our vertex, line of symmetry, symmetry. And then do make note that if we ever have a line of symmetry, that because it's vertical, we would always write that x equals 0 in this case because that is that vertical line that marks the line of symmetry. I should also note that x-intercepts, I know that you guys probably know this, but x-intercepts, I'm just going to call them x-ints, these are the points where the parabola crosses the x-axis. Okay. So again, I know that you probably have a feeling of knowing this stuff already, but it's really good to note. So here our vertex is actually our x-intercept, so you can see that there. That point is 0, 0. Over here, if you were to mark this, our points are 1, 2, 3, 3, 0, and then -2, 0. So one thing to note is that you might not know where the parabola crosses the x-axis, but that y is equal to 0, or in other words, f of x is equal to 0. The whole function, where is the function equal to 0? Well, those are what we call the x-intercepts. Alright, a quick and general check. When we are graphing these, you're always going to want to look at the a, and the a is just the number out front of the x squared. It's the coefficient or the multiplier on the x squared part of these quadratics. If a is negative, what we have is a sad face. Okay, sad face. Right, so you can notice here that a is equal to -1. That would be the coefficient attached to the x squared. Note here that a is equal to -2. Alright, sad face again. Oh. And then here we have a equals -0.5, and again we have a sad face. Note all over here that we have positives. A is equal to 0.5, a is equal to 1. So here we have happy faces. Okay, so it makes sense. Positive, happy, negative, sad. Right? That's just sometimes a good check. After you've graphed something, go back and look at your A and see, okay, should I have a happy face or sad face here? This, I imagine, is going to take you a while to copy down. I would suggest doing it. It's a good organization system. But this is one form of quadratics we have, second form, third form in no particular order. But we have three very prevalent forms of quadratics that are very helpful to graph. So go ahead, write that down. But otherwise, I'm going to step you through it. So the vertex form, hopefully this isn't too new to you. This is actually our shifted transformed parent function. You'll notice that this is how much left our parent function goes, left or right, and this one's how much up and down our parent function goes. This is that scalar multiple, that a, that is either going to flip it if it's negative, but otherwise stretch or shrink it. The vertex is, wherever this tells you to go left or right with the vertex, the new location of that vertex is going to be at h, k. Note h is the opposite of what you would think. Like I said, think shifts. Okay, so here, if you had the original parent function, x squared, what we know is we would take that vertex and we would go left 4, so back 1, 2, 3, 4, and then down 1. There's our new vertex, so you can see our new vertex would be there. Alright, so the solutions, or in other words, these are also what we call x-intercepts. The vertex form, of course, is very strong in helping us find our vertex when graphing. Finding the x-intercepts, not so strong, but it's okay. You just set y equal to 0, because remember, those x-intercepts are where our function crosses the x-axis, and of course those y values are 0, no matter where that parabola is on that x-axis. They have to be 0. So for the vertex form, you just set it equal to 0 and solve for the x using SAD-MALP, or the backwards order of our order of operations. Standard form, vertex, we get our x value of our vertex. If it's in standard form, the a is the coefficient attached to x squared, b is the coefficient attached to the x, and c is just that constant. And so what we would use is this formula right here, a very helpful formula. X equals negative b over 2a. And what that does is it finds the x value of the vertex, and then of course to find the y value, you just have to plug that x value in to find the corresponding y that goes with it. Okay, so it's okay, standard form is okay for finding the vertex as long as you use that formula and you got that down. It's a very simple formula to follow if you have it in your mind. Solutions. Once again, standard form, it's okay for finding solutions, or in other words, the x values of your x-intercepts. What you do is you would set y equal to 0 and solve for x using what we call the quadratic formula. Remember this. I do have a song. I'm going to sing it. So x equals opposite b plus minus square root b squared minus 4ac all over 2a. That's how you can remember that quadratic formula. Okay, so keep in mind that weird decimals may occur. That's going to happen. And then factored form, this is our last one that I'm going to talk about for quadratic forms. We have that a again, don't forget about that a, and then what we have are these two things that we call factors. The vertex, it's okay. I actually normally take factored form, FOIL it back into standard form, and then just get my vertex that way. But otherwise, the strength of factored form is finding our solutions, or in other words, our x-intercepts. Just set each one of those factors equal to 0. So you would set this factor equal to 0. 2 can't be set equal to 0, but x minus 10 can be equal to 0. X plus 3 can be set equal to 0. Solve for those values, so x minus 10 equals 0. When you add 10 to both sides, what you're going to get is one of our solutions, or one of our x values of our x-intercepts. Alright, same thing here. If you set this equal to 0 and solve for x, you would get negative 3. So that's our solution, or the x value of our x-intercept, and this would be our x-intercept. Here are some general steps for graphing. You don't have to memorize these. I hope that they kind of start coming naturally as we do these more. Alright, so an example of this is number 5. The instructions for number 5 is they give you a set of graphs and then they give you a set of equations, and they want you to match up the equations to the graphs given. So let's just look at this number 5 here. I'm going to just do a sketch of it, knowing what I know about all this. So when we're looking here, we can kind of see this almost, it's not standard form, it's not factored form. What it's close to is our vertex form, but note that this is a little bit backwards. So I am going to do a plus and then negate this. Okay, and if you want to, you can even go so far as, because this is addition, we can take those two terms and then just commute them. So here, because the order of adding doesn't matter, we have negative x minus 2 whole quantity squared plus 4. Right, so now this is our vertex form. So what this tells us right here is, because it's not with the x, it's a vertical and it's negated, flip. Okay, there is no stretch factor here or shrink factor, so we're just, because it's 1, it doesn't stretch or shrink it. This thing right here is addition or subtraction. You think addition or subtraction, you think shift. And because it's directly attached to our x, it's a horizontal shift. Okay, and it's opposite of what you would think. It's to the right 2. And then this thing, once again, addition or subtraction, not being squared with the x, not being with the x. This is then therefore a vertical shift, and it would be up, exactly what we would think for. Okay, so let's just go ahead and quickly sketch this. I know my vertex then is at 2, 4. So I'm going to go forward 2 and then up 1, 2, 3, 4. Alright, as outlined, when we're graphing this, you can either use the A, so let me look at these steps real quick. So we're using vertex form. You can use A, or set up an XY table, or find x-intercepts. So you could always find the x-intercepts here if you want. I'm going to set this function equal to 0, just so we can get some practice in on doing this. And we could solve for this x. So keep in mind SAD-MEP is what we use. Any subtraction or addition not in the parentheses we're going to undo first. So minus 4, negative 4 equals negative 1x minus 2 squared. Any division or multiplication not in parentheses, we're going to undo that. So I had that multiplication of negative 1 out there. Okay, we're going to undo any exponents. So I'm going to square root. So keep in mind this is plus minus 2 equals x minus 2, and then when we add 2 to both sides, what we're going to get is 2 plus 2, which equals 4, or 2 minus 2, which equals 0. So these are our solutions, or in other words, the x values of our x-intercepts. X-intercepts are the points, so these are the points that I could plot. Okay, so there are my x-intercepts. You could also note that this was just down 1, so instead of doing the parent function over 1 up 1, we can just go back 1 down 1. And then likewise in the same direction, opposite direction, same distance, because it's that vertical line of symmetry, we could draw those points to represent that 1. Had this been 2, negative 2, we would go over 1 down 2, over 1 down 2. Okay? Otherwise, you could always set up an XY table. Once you have that central piece, that vertex 2, 4, you could always just plug in values 1 to the left, 1 to the right, and you would have gotten that as well by plugging it into the equation. So this one actually ends up matching up with F. So in your book, they have a graph. They labeled it F, and it looks like this, so you can see that we nailed it. Alright, 54, this example, what it asks you to do is determine the x-intercepts of the graph visually, then find the x-intercepts algebraically to confirm your results. So if you looked at this, you can actually see that the vertex is sitting right at the origin, or right at the x-axis, and so this thing right here is going to be 3, 0. So we're looking for x-intercepts that are 3, 0. So how would you check this algebraically? We've looked at it visually as the directions instructed, and now we have to verify it algebraically. So first of all, I want to show you also that the vertex lies there, so we would do that vertex calculation. X equals negative b, which is negative 6, so b is our negative 6 right here, plus negative, and then all over 2 times 1. So we would have negative 6 is of course positive 6 divided by 2 equals 3. And then what we would do is plug that value x in for the x. So 3 squared minus 6 times 3 plus 9, what we're going to get is 9 minus 18 plus 9. And when we simplify that, we're going to have 9 plus 9 is 18 minus 18 is going to be 0. Alright, so there's our vertex. 3 is our x value, comma 0 is the y value that went with it when we plugged in. So that verified that. The other thing is we could also find the x-intercepts. So how would you find the x-intercepts? Well, again, we're looking for when is y equal to 0. So set that thing equal to 0, and this is what we're really going to want to recognize is whenever we have a quadratic set equal to 0, you can do a couple things. You could try to factor this, alright, which it is factorable. We're looking for two numbers that multiply to be 9 and add up to be negative 6. If you think about that for a moment, negative 3 should come to mind, right? And we need two negatives to make this positive, and plus we wanted to make this negative, so that is going to work. We have x squared if we check this, and then minus 3x plus 9, which is exactly what we wanted. So we set each one of those factors equal to 0, which we are going to get the same answer here because they're the exact same. So x equals 3 and x equals 3. This is a duplicate 0. We'll talk about these later, but there you have it, and there we can see, yeah, that verifies it. Otherwise, what you can always do is if you ever see a quadratic equal to 0 or set equal to 0, we always want the quadratic set equal to 0, we can use the quadratic formula because the quadratic formula will get us those x values of our x-intercepts if you ever have that situation. So we have negative b, which is negative 6, plus minus the square root of b squared, which is going to be that negative 6 squared, minus 4 times a, which is 1 times c, all over 2a. Okay, so here we would have 6 plus minus, and then I'm going to simplify 36 minus, and then 4 times 1 times 9 is 36, all over 2. So we have 6 plus minus, we're going to get the square root of 0 all over 2. So this is again going to get us, well, those x values of our x-intercepts are x equals 6 divided by 2 plus 0 and 6 divided by 2 minus 0. So it's just going to be x equals 3. Okay, just like we confirmed visually, algebraically, in a couple different ways. Alright, there's your homework or there's your practice. Good luck.